Hey guys, in this video I wanted to review some practice problems related to reactions involving enols and enolates. These are alpha functionalizations of carbonyl compounds, since we're going to be putting a new group, an electrophilic group, at the alpha carbon of a ketone or aldehyde typically. And this is based on LTQ 8.1 in the spring 2024 semester. All right, so in this first problem, we're asked to predict the major neutral product of each reaction and draw the enol or enolate intermediate that leads to this product. So we want to do a little bit of mechanistic reasoning here, thinking about where deprotonation of each ketone or aldehyde is likely to occur based on the base used and the reaction conditions, etc. And then what is that enol or enolate going to do with the other reagent that's used? So right here in the first problem, we have a ketone. We've got a cyclohexyl methyl ketone, and that's being combined with LDA, which is lithium diisopropyl amide. Now, LDA is the lithium cation together with a nitrogen anion, and that nitrogen is linked to two relatively large isopropyl groups. So this is a bulky kinetic base. This means that deprotonation is going to occur selectively at the less substituted position, leading to the less substituted enolate. And I'm going to go ahead and draw that out since that's part of the problem. And this is a mechanistic intermediate on the reaction pathway that's important to consider. And this is one resonance form of the enolate, completely fine to draw the other resonance form of the enolate, and it may be worthwhile to pause the video and go ahead and draw that alternative resonance form if you want more practice with enolate resonance structures. Now, what is this going to do with the alkyl halide substrate, the alkyl iodide introduced in step 2 of this reaction? Well, the enolate is nucleophilic at carbon. We know this, and we've seen countless times at this point, by this point in organic chemistry too, that alkyl halides are electrophilic at the carbon linked to the halogen leaving group, linked to the iodine in this case. And so this is a dead giveaway for an SN2 type reaction between the enolate of this ketone, the kinetic enolate, the less substituted enolate, and the alkyl halide. And the only thing here to be careful of, a little bit careful of, is just to count carbons, right? 1, 2, 3. And you want to make sure to include all these carbons in the product, 3, 2, and 1. And let's just label those carbon 3, carbon 2, carbon 1. So we have indeed included all the carbons of the propyl group in the product, and this would be our final product, monoalkylation product, at least. We've seen other ways to do this, but this is our best guess with one equivalent of LDA and one equivalent of the alkyl halide. Now, in the second reaction, we have bromine, Br2, elemental bromine, and sodium hydroxide reacting with this ketone. An important thing to notice about this ketone is it has only one enolizable alpha carbon. There is only one alpha carbon that has a hydrogen that can be deprotonated, and it's right here. And we do have a good base under the reaction conditions in hydroxide. Not great, but good enough to generate an enolate intermediate at least reversibly. And there's really only one enolate intermediate that's possible here because of that one enolizable alpha carbon, and it has a structure that looks like this. Again, I'm drawing the C- resonance form just to emphasize that that alpha carbon is nucleophilic. And in asking where we go from here, we're looking for electrophilic atoms among the other reagents. And Br2 is an electrophile. You can think of this as a bromine linked to a good leaving group. This makes Br2 electrophilic at one or the other of the halogen atoms, and so we can do these alpha functionalization reactions when an enolate is combined with a halogen like Br2 or Cl2. And so our first inclination would be to do something similar to what we did above, a kind of SN2 process here, where we substitute the H ultimately for a bromine, and that leads to this monobromo product here. The problem with this, not really a problem, but something we want to consider, is that there are two more H's here, and these are now more acidic than the 3 H's in the starting methyl group of the starting ketone, right? Because Br is electron withdrawing and exerts an inductive effect that's going to stabilize the enolate derived from deprotonating, for example, here. And so a second round of halogenation can occur and will occur more rapidly than the first. And so this is going to uncontrollably put a second bromine on there. And now that last H is even more acidic than the previous two. And so that last H will be very rapidly deprotonated by hydroxide in the reaction mixture. You'll sometimes see excess used with the reagents to emphasize we've got more than enough hydroxide around to do this. We would want this practically. We would use excess hydroxide pretty much regardless to ensure the reaction goes to completion and we get high yield. And we get to here, and now we're out of alpha hydrogens to deprotonate. And so a number of people thought, okay, reaction stops here, I'm done. However, what we've done now that we have 3 electronegative bromine atoms connected to this carbon is we've created a good leaving group, a decent leaving group in this CBr3- anion, right? And we have a good nucleophile. In fact, we already recognized it as a base in the hydroxide anion. And so hydroxide can actually displace the CBr3- anion in a kind of nucleophilic acyl substitution or acylation process. You can think of this as an acylation of hydroxide. And we would actually end up initially with this carboxylate anion and the conjugate acid of CBr3- HCBr3, or bromoform rather, with the 3 bromines. Now, what we would actually do to get a neutral product out of these reaction conditions is work up the reaction with acid. That's going to protonate our carboxylate anion, give us a neutral carboxylic acid. So both of these products are formed. Typically, we don't care as much about the haloform byproduct. This is an example of the haloform reaction. And so typically, we would just draw the carbonyl-containing product, which is here, the carboxylic acid. So this halogenation under basic conditions, if we've got a methyl group around, this will go all the way to the corresponding carboxylic acid due to the ultimately profound oxidation that's induced by this Br2 reagent and the electronegativity of bromine. All right, here now we have cyclopentanone combined with benzophenone in the presence of sodium metal and ethanol. Now, an important point about the sodium metal and the ethanol. This is sodium 0. This is not sodium cation. This is a lump of sodium metal. If you've never seen sodium metal, for example, the reaction of sodium metal with water, fun thing to look up on YouTube. What will happen when this very strong reducing agent comes into contact with the alcohol is H2 will be formed as well as Na plus and OET minus. And so let's go ahead and write that, since OET minus is going to be our really active species here in terms of doing the business. OET minus is a decent base, decent enough to generate an enolate reversibly at least. And here we have only one unique enolizable position. The phenyl rings in benzophenone do not have any hydrogens at the carbons directly linked to the carbonyl group, right? Because there are benzene rings there. There are 4 bonds to carbons, a double bond and a single bond at that alpha carbon linked to the carbonyl carbon. So without any alpha hydrogens, this cannot form an enolate. The only enolizable position is one of the alpha carbons of cyclopentanone. And those are equivalent. We'd get the same enolate regardless of where we deprotonated, and that's going to be the enolate of cyclopentanone, which in its C- resonance form is going to look something like this. Awesome. Okay, so here's our enolate intermediate. Now the question becomes, how is this going to engage with the benzophenone, the remaining ketone? Well, the benzophenone can really only act as an electrophile because it's non-enolizable. And so our first thought should be some kind of nucleophilic addition of this nucleophile to the electrophilic carbonyl carbon. That's exactly what's going to occur here, and that's got a name. We call that the Aldol reaction. And initially what we'll get here is exactly this nucleophilic addition. So we'll have cyclopentanone. We'll have a new bond to the carbonyl carbon of benzophenone. That carbonyl carbon is linked to 2 phenyl rings and an oxygen, and initially that will form an alkoxide anion. We can imagine protonating that with solvent ethanol, for example, and we would get this neutral beta hydroxy ketone. A number of people drew this, but one thing to keep in mind is that when we have the potential to generate a highly extended conjugated system with delocalization over a large number of atoms via elimination of an H from the alpha position and OH minus from the beta position, H plus essentially from the alpha position and OH minus from the beta position, this will happen spontaneously. And this is exactly what happens under these reaction conditions. We end up with a double bond between the alpha and beta carbons, an alpha-beta unsaturated carbonyl compound. And I'm going to clean this up a little bit to make the bond angles look nice. We'll have a double bond here and two phenyl rings connected to the beta carbon. And what happened to the carbonyl oxygen in benzophenone? Well, it was lost as H2O, as water, right? And so via an E1CB type elimination mechanism, we get this alpha-beta unsaturated carbonyl compound. And this is an example of what we call the Aldol condensation, since water is lost as a small molecule in this reaction. All right, last but not least, we have this ketone in combination with sodium ethoxide base in the first step and an alkyl halide in the second. So in the second step, I'm already thinking about alkylation, thinking about SN2 reactivity at that carbon. The question is, what's the nucleophile? Where am I going to deprotonate? And this is an interesting ketone substrate because I've got two potential acidic positions. I've got two alpha carbons that are not the same. Let's number these carbons just to help us keep track of things a little bit. Notice that carbon 2 is alpha to the carbonyl group at carbon 3 and also is linked to a methyl group. Carbon 4 is also an alpha carbon and is adjacent to the carbonyl group at carbon 3, but also the cyano group at carbon 5. And that cyano group is electron withdrawing. This is a C-N triple bond. Let's actually draw this out to emphasize this point, that if negative charge appeared at carbon 4, it would be possible to delocalize that negative charge into the cyano group. And curved arrows like this give you a sense of how this is possible. This gives an extra resonance form to the enolate formed by deprotonation at carbon 4 relative to the enolate formed via deprotonation at carbon 2. And so the major enolate under these reaction conditions by far is the one derived from deprotonation at carbon 4 between the two electron withdrawing groups. And here's a full structure for that enolate. A good opportunity to pause and draw both. There are two important alternative resonance forms of this anion that are worth recognizing. The other enolate, which you may want to pause and draw out on your own, only has one, the other typical enolate resonance form with negative charge on the carbonyl oxygen. Okay, now that we've identified this enolate intermediate, well, our mechanistic reasoning is well on its way. That's a nucleophilic atom that can displace a bromide leaving group in an SN2 process. And the product we will get is going to have a new benzyl group connected to that carbon that we deprotonated to generate the more stable enolate. So again, we have carbons 1 and 2. That ethyl group continues undisturbed in the reaction mixture. And let's go ahead and number carbon 6 and the phenyl group number 7. We have a new bond here between carbon 4 and carbon 6. It's an alkylation process taking advantage of the enhanced acidity of carbon 4 thanks to it being kind of a doubly alpha carbon between two electron withdrawing groups. In this problem, we're essentially asked to apply the aldol reaction retrosynthetically. We've got a stockroom, quote unquote, of these 10 aldehydes or ketones, and we're given 3 targets. We see one in the bottom right. We'll see the other 2 shortly. And for each of those targets, we're supposed to work backwards to the nucleophile and electrophile that need to be combined to produce that target. Now, in general, the aldol reaction is going to involve an enol or enolate nucleophile and a ketone or aldehyde electrophile. And a key point is that on the electrophile side, because a nucleophilic addition occurs, the carbonyl group is transformed into either a hydroxyl group, we get a beta hydroxy, ketone or aldehyde, or water is eliminated all together, and that carbonyl carbon becomes the beta carbon of the alpha-beta unsaturated enone or enal product. And so to identify the nucleophilic and electrophilic side, when we're dealing with alpha-beta unsaturated carbonyl targets in the aldol reaction, the beta carbon will be associated with the electrophile and the alpha carbon with the nucleophile, since after all, on the nucleophile side, since an enolate is involved and the enolates carbonyl, carbon, and oxygen are not directly involved in bond formation or cleavage, the carbonyl group is retained on the nucleophilic side. So let's talk through what I mean by this in specific terms using this example in the bottom right. So we have here an alpha-beta unsaturated aldehyde right here. And based on what we just said, we can recognize, well, first of all, let's recognize this is the alpha carbon relative to the aldehyde carbonyl group, and here's the beta carbon. Based on the logic we just worked through and the mechanism and sort of the structural patterns built into the aldol condensation, the beta carbon is going to be associated with the electrophilic carbonyl partner, here a ketone since we don't have any H's linked to the beta carbon, and the alpha carbon is that carbon that is nucleophilic, that was the nucleophilic anionic carbon in the enolate reactant. And so using this idea, we can sort of split at the carbon-carbon double bond. One point I like to make about this in class is that this was, prior to the invention of the Wittig reaction, this was the most popular way to make carbon-carbon double bonds. It was particularly attractive because both bonds are made in one reaction. We're not doing, for example, an E2 or E1 elimination where we already have a single bond between the atoms that we want to link via a double bond. We can make both bonds in one pot here. And the nucleophile is going to include that aldehyde group as well as a methyl group. That methyl carbon is the carbon that is deprotonated to generate the enolate intermediate, if we're thinking about basic conditions here, that leads to this target. Now on the electrophile side, you want to think about essentially adding water and then moving some protons around to put a carbonyl group at that carbon highlighted in blue, a carbonyl group at the beta carbon. So the two phenyl rings are present on the electrophilic side, and a carbonyl group is there. And one thing to notice, now that we have both of these structures down, is that what's missing from the product or the target relative to the starting materials are two H's. There is an H remaining at the alpha carbon in the target, but two H's are missing, as well as the carbonyl oxygen is missing, the elements of H2O. So this target is made via an aldol condensation of these two reactants, and these are, what are the letters of these? This is A, acetaldehyde, and on the electrophile side we have benzophenone, which is G. Awesome. All right. It's possible to do two aldol condensations in one reaction mixture if you've got a diketone or dialdehyde substrate involved. And as above here, we can recognize here we've got two alpha carbons, alpha-alpha, and two beta carbons, and both of those double bonds can be constructed using aldol condensations where the carbonyl side, or the alpha side, the carbons closer to the carbonyl group, are the nucleophilic side, and the two beta carbons are associated with carbonyl groups. So imagine a carbonyl here and a carbonyl here, and we can work backwards to the starting materials needed to make this. So on the nucleophile side, we're going to have two methyl groups. Each of those methyl groups is deprotonated to generate an enolate in some sequence of steps that's a little bit difficult for us to predict a priori, but sort of as long as we step through this logically, it makes sense, right? We make one beta hydroxy ketone, then maybe make the other, then eliminate water from both to get the target, something like that. But point is, we can make enolates at both of those methyl groups, and this will lead to the target. And then on the electrophile side, we need two carbonyl groups to make this work. So we're going to have the two carbons kind of at the base of the five-membered ring in the target, and each of those is going to have a carbonyl group associated with it. And so here's our electrophilic carbons, our two nucleophilic carbons we already highlighted, and then among our stockroom of reactants up here, it looks like I messed up. because we do not have a dicarbonyl compound that fits the pattern of the structure here in the electrophilic structure in this second problem, but we do have acetone. That is D. That is structure D. Awesome. Okay, let's look at the last example. So last example, we've again got an alpha-beta unsaturated carbonyl compound as the target. Here's our beta carbon. Here's our alpha carbon. And as usual, we're going to think about the alpha carbon as the enolate side, the nucleophilic side, and the beta carbon as the electrophilic side. And so our nucleophilic reaction partner here is going to be cyclohexanone. Imagine deprotonating this alpha to the carbonyl group to generate an enolate right here, for example. And then on the electrophilic side, one thing to note about this beta carbon is it has an H linked to it. And so our electrophile here is going to be an aldehyde. Specifically, it's going to be acetaldehyde, which has this structure and which is reactant A. And cyclohexanone we have, that is reactant E. Nice. Okay, and again here, our electrophilic carbon is there. And we can imagine the target forming through, for example, a base-promoted aldol condensation, where we make an enolate intermediate here, for example. We could do this with directed aldol, right? We could use LDA to make the enolate of this, add in A, and then work up with acid or heat and base over time to get the alpha-beta unsaturated carbonyl compound. This one requires a little bit of extra care because unlike in the first two cases, we have the possibility of a problematic crossed aldol situation, right, with an enolate possible here or here. To avoid that, directed aldol condensation would be the way to go here.